Welcome once more to our videos in Mathematics 2. We've introduced the first algorithmic approach to local optimization. That was gradient descent. And today we're going to look at an alternative method, that is Newton's method for optimization. So you remember that gradient descent, the main idea of gradient descent was to take a small step in the direction of the negative gradient. And you could interpret that as a linear approximation of the function and then minimizing that linear approximation. Of course, we are not limited to linear approximations. You know, we have Taylor's formula available to us. So it is totally possible to do approximations of a higher degree. And as long as we can minimize those, it would also be possible to use them to get a possible direction for the minimization of a more complex function. So to summarize, gradient descent uses a linear approximation of f locally and minimizes that. And for Newton's method, we'd like to try a little bit higher orders. So we'd like to go to order 2 and see if we can still handle that minimization. Okay, so what we want to do is we want to use a quadratic approximation instead of a linear approximation. So could we use a quadratic approximation? Instead of a linear one, and hope that this yields better results? Yeah, and of course we can. We just have to have a look at the Taylor polynomial of order 2 of f at x and our current or initial point x0 or current iteration xk. So in general, what does that look like? Let's see. So 2ff of x and xk for some iterate xk. You know Taylor's formula, that would just be the function value of f at xk plus the gradient of f at xk transposed times x minus xk plus 1 over 2 x minus xk transposed times the Hessian of f at xk times x minus xk. So that's the Taylor approximation of order 2. And now the task would be to find a stationary point of that Taylor approximation. Or of course, what we'd like to do is we'd like to find a minimum, or if you want to maximize, we'd like to find a maximum of that Taylor polynomial. So for a stationary point, what do we have to do? We just have to set the gradient of that function to 0. So we want the gradient of t2f of x and xk, and we want that to be 0. If we look at this function f, this function t2 here, it looks like this. So we need the gradient of that function, and that's easily computed. Gradient of that function, if we do that, then this is just a constant that vanishes. So here's an x. That means we will be left with just this gradient term here. And here we have two x's and a 1/2. And we did an example where we differentiated a function like that. So you know that the result is basically the Hessian times one of these x terms here. Okay, so that gradient, that looks like this. What we get is the gradient of f at xk plus the Hessian of f at xk times x minus xk. And that means there's only one x term in here. So we can reformulate that in a way that puts all these x terms here on one side, like this. hf times x minus xk is then equal to minus the gradient of f at xk. Yeah? So remember that expression has to be equal to 0, and we just reformulate that a little by putting this constant gradient on the other side of the equation. And this is what is called Newton's equation. So that's this expression here. That is called Newton's equation. And basically what we want to do is we want to determine this expression here, x minus xk, and then we want to move to the new x that solves this expression, that minimizes, locally minimizes or maximizes this quadratic approximation. So our xk plus 1 is going to be the x value here, this one. And we can express that simply as xk plus x minus xk, right? So once we solve for this expression here, then we can determine the next iterate xk plus 1, but just adding that to the current value of xk. And this is better in terms of function values. We would expect that to be better in terms of function values if this hf of xk is positively finite for minimization. Because then we compute the local minimum of the approximation, and hopefully this will also yield a better value for our original function. Right? Okay, so that kind of summarizes Newton's method already. Let's write down the algorithm formally. So again, the input is similar to gradient descent. We just take a function f. The difference is this time we need that function to be 2 times continuously differentiable, because we also need to compute the Hessian. And of course we want to do that on r to the n. And again, we need an initial value, x0, which is just some point in R to the n that we start with. And the expected output is either a value x star that approximates a local minimizer, of f, or we can also report that the Newton's equation cannot be solved. We haven't looked into that possibility yet, but it might be that we just cannot find a solution for this equation. Or report that Newton's equation cannot be solved. So we have to incorporate that possibility, of course. And formally, we do pretty much the same thing as in the gradient descent first. We start a counter. We initialize that at 0. And then we have a while loop that's going to run as long as our current iteration has a gradient that is not 0. And again, we could also impose the condition that the norm of the gradient is above a given threshold. So once it's close enough to 0, we could be satisfied because we only want an approximation anyway. So while that is the case, we do repeat the following steps. We find a v in R to the n that solves Newton's equation. And that equation is hf at xk times v is equal to minus the gradient of f at xk. So we solve this linear equation system for v. If that is not solvable, then we terminate and report the failure. If it is solvable, then we set xk plus 1 to xk plus v. Yeah, so we move to the minimum of that local approximation. And similarly to gradient descent, of course, we could also say, well, let's maybe not move the whole way to this local minimum because it may be too far away and the approximation may not be that good anymore. So let's just move a little step in that direction. It's probably a good idea to move in that direction, but maybe not just that far. So as an alternative, we could also say, let's determine xk plus 1 as xk plus some step size lambda times v for some step size lambda. And again, the selection of that step size is an art in itself. You can pretty much use the same methods as in gradient descent if you want to do that. And once we have our new point, we just increase the counter k by 1, and that ends our while loop. And then finally, we just return x star, and that's the last value of our iteration, so that's the last xk. Okay, so this is the idea of Newton's method. And again, we'll see an example to see how it compares to gradient descent in one of the next videos.